everybody. So I'm picking up where I left off in the last video. I'm actually using a different screencasting software and a different microphone setup. So if you can notice a difference between the last video and this one, if you have any feedback on what worked better, what sounded better, or anything like that, please let me know. I am still working on this and it's going to take some practice. So this is where we left off. Luminosity of the sun being 3.84 by 10 to the 26 watts. And I mentioned at the end of the last one that we experience this as brightness. When we look at the stars, we're seeing this energy being released and our eyes interpret it as light. So this is a graph that looks at then how different temperatures of stars, so all of these numbers along the tops of the graphs, how the temperature of star affects what kind of electromagnetic radiation it releases. So down here at the bottom, all of visible light is right around 500 nanometers in wavelength. And what's along the y-axis is the intensity, or how much of each wavelength of light is present. So our sun is actually right here. Oh, pen's not working. Our sun is actually right here. The temperature of the sun is about 4,500 degrees Kelvin at the core. There's my little symbol for sun. And what that means is that if I trace the peak of this curve downward, most of our sun's energy being released is in a wavelength in the red and infrared sections of the electromagnetic spectrum. You may want to go back and remind yourself of what the EM spectrum was and how it, the names for the different parts of it. So this is very convenient, all things being considered, that the peak of our sun's radiation is in the visible spectrum, or just off of it, and that's what we can see. That's what our eyes and brains interpret as visible light. So some stars that are much lower temperature, their peak is off visible. So it doesn't mean we can't see them. It doesn't mean that we can't interpret the information. We would just need a different kind of telescope. We would need to use something that reads infrared or reads radio waves. One of the major projects I did in undergrad looked at using those because of light pollution. It's very hard to see stars in the middle of a city when there's so much light pollution from buildings and street lamps and everything. So you just need a telescope with a filter that's going to read different wavelengths, and then a computer that can interpret that into something we can understand. Stars that are hotter than us are going to have their peak more towards the blue and purple end of the electromagnetic spectrum. We don't really see any purple stars. We usually go about as far as blue. And one of the activities you're going to do later in this lesson looks at some of the connections between the color of the stars and their temperature, which is why I put this graph in now. So for the last part of this lesson, we're going to look at the nuclear reactions that are happening in different masses of stars and at different points in a star's life cycle. So the bulk of the stars that we see when we're making observations are what we call main sequence stars. And what we mean by main sequence, or what the definition of main sequence is that they're in the period of their life. Life is kind of not the best word here, but it's the best one we have, where hydrogen is fusing into helium. And that happens for the bulk of the star's life. You have that center, that gray section of the star right in the center, where the helium that has been formed sinks into the middle, and the hydrogen burning is happening in a shell around it. The rest of that picture, non-burning envelope, is there because that's the hydrogen material that's not reacting at this point. The temperature and pressure aren't high enough in the outer layers of the star to have fusion happening. It only happens right in the very core. These stars are in equilibrium. They're very, very stable. You have this fusion happening in the center that's releasing a lot of energy, and it acts like an outwards pressure. It's like the core of the star. You'll notice that my art skills have not improved in quarantine. And that's acting against, this would be the yellow part, what would be the gravitational collapse. Gravity wants to pull everything inward towards the center of the star. but that pressure caused from the energy being released by fusion acts outward, and the star is in equilibrium. These two are balanced. So these stars are very, very stable, and they can go on for quite a long time like this. For most of their lifespan, about 90% of a star's lifespan happens while it's on the main sequence, and this is all that's happening. And it's kind of, I don't want to say boring, but it's not the supernova, it's not the black hole, it's not that sort of exciting end of days kind of aspects of a star's life cycle. This is very good for us because it means that the sun's energy output is relatively constant. We have a approximately constant temperature on Earth. We have seasons because of the tilt of the Earth towards and away from the sun. But all things considered, life is fairly straightforward and fairly easy for us because the sun is very stable. When this is done, however, when this star reaches the point in its life when the hydrogen in that core right around the center has finished, there's no more burning happening, there's no more fusion, and this outwards pressure here ends up going away. And so I had this nice balanced picture of equilibrium between the gravitational forces and then that outwards pressure. Once fusion is done in the center, there's nothing keeping it from collapsing. So this material is all going to collapse inwards because of the gravitational forces. What that means, though, is that the temperature increases and the pressure increases. It's now hotter than it was, it's now denser, it's now much higher density, which means that it can start fusing helium. It wasn't hot enough before for helium to go on to the next step, but now it is. So once we start helium fusion, begins, we reintroduce that outwards pressure. So the star expands in size. I'm realizing I'm talking with my hands and you can't see me. That's great. We had a nice stable star. My hands are about as wide as a basketball, which then collapse. Now I'm a baseball. And then when helium fusion begins and we have that outwards pressure in, it expands much, much larger, think like a beach ball. So the size increases of, the size of that star increases as well once we move on to helium fusion. Because the energy being emitted now is much, much, much higher than it was before. If we were to go through and get the mass defect and to calculate the energy released, it would be much, much more than it was during the main sequence part of its life, where we were creating helium from hydrogen. So what happens next really depends on the mass of the star. Some very, very small stars don't even really have this core. They're sort of burning hydrogen into helium throughout, and it's sort of like a soup that's mixed up. It doesn't have this core aspect. What our sun is going to do, smaller stars like our sun, they are going to have this helium burning shell that's the light blue, not the dark blue right in the center, but the sort of teal color around it, where they will, oh, I'm still red, take helium, takes 2 helium nuclei. This isn't all of the steps, like when we did the broken down calculations for hydrogen. This is just sort of the net step to create beryllium, which is going to release gamma rays. Beryllium plus another helium is going to create, see if you can guess, just based on keeping the nuclear equation balanced. And carbon plus another helium is going to end up at oxygen. So our sun is not here yet, but this is where it's going. At each stage, helium creating beryllium, beryllium leading to carbon, and carbon leading to oxygen, it goes through that same process where it's stable in equilibrium. It's bigger than it was before. One step ends, it collapses, which increases the temperature, which increases the pressure, which can start the next step, which will blow it up again. So at each step, you have something equilibrium, which gets smaller, which expands, which at some point in its future will collapse, get hotter, get denser, which will expand, which will collapse, which will expand. Now it's off my page. So you get these massive, massive stars. These are the red giants. So eventually the sun is going to envelop the Earth. It will be big enough that it will take over the orbits of the inner planets as it gets to this phase in its life. Chances are the Earth will be inhabitable long before that because of the temperature increase of the sun. So we can't get all the way to iron. Our sun's not hot enough. It's not got enough pressure. It's not got enough material. So a larger star, for very, very massive stars, end up with this sort of layer cake kind of aspect to them, where they'll go beyond carbon. They'll take 2 carbons to fuse neon and have helium as an output. They'll have 2 carbons to form magnesium. If you're interested in the specific reactions, that game that was kind of like 2048 that I pulled up on my screen before spring break will show all of the reactions involved in this. That was the one where you had to try to get to iron. You have lots of spare time on your hands right now, guys. Go play it. So as this happens, the heavier elements are going to sink down into the core. So we get iron in the very center there. And then layers of materials: silicon, magnesium, neon, oxygen, carbon, helium, hydrogen, and then the outer envelope. So it does not continue past iron. And we talked a little bit about this before spring break because that's a reaction that requires energy rather than emits energy. And a star is not going to do something that requires energy because that's self-destructive. It will end up, it will end up burning out the star instead of doing something that creates energy. This is that graph that we looked at before that explained why. When we're looking at fusion on the blue side of the graph here, we're headed up this direction. Iron is at the peak here. And fission, which isn't relevant right now, but we talked about before the break, heading that way, also ends at iron, because to split apart to something smaller than iron also requires energy. So iron's kind of the peak of the curve here, and this particular isotope is the peak of the curve. So this is the kind of star that will end in a supernova. It's going to go through that same process of being a size and collapsing and expanding and collapsing some more and expanding some more and so on, until it reaches the very end of its lifespan when iron is created. Iron is in the core. No more nuclear reactions can happen. And then the star is just so big that that collapse into the center as a massive rebound of material. Kaboom. Which releases a huge amount of energy in an explosion. This is hot, this is dense on a massive scale, and this is when we can get material beyond iron. So this is a view of the periodic table based on where the elements come from in the first place. Because the question is, if fusion only happens up to iron, how do we get the larger naturally occurring elements? So uranium is the most massive element that occurs naturally. Iron is the biggest nucleus that we can create through fusion, but we have naturally occurring elements all the way up to uranium. So these come from fusion that happens when other events are happening. So when you have neutron stars merge, which is also one of the sources of gravitational waves, when you have these exploding stars, that energy being released is enough to cause fusion to happen on a larger scale, to go beyond iron, because at that point it doesn't matter if it's taking in energy, it's not self-destructive anymore. So we have hydrogen and helium that come originally from the Big Bang, from fusion that happened just after the Big Bang, as well as in smaller stars. We have helium through iron happening in the cores of stars, and then iron through uranium happening in supernovas or neutron stars. This is just kind of a neat graphic of where we see the origins of the different elements. 43 and 61 are lab-based. They don't occur naturally. That's why they're gray like that. So I hope you have learned a little something about the fusion reactions that happen in stars. If you have any questions, feel free to reach out during the office hours. The Google chat function is the fastest way to get my attention, but email will work as well. Even if it's not questions about the material, this really is the area of physics that I'm most interested in and most passionate about. So even if you just have that, but what about this kind of question, or that sort of more esoteric side of like, how do we know this stuff, or where do we think the universe is going to go in the end? I love talking about this. It is maybe actually a good thing we're not doing this in class, because it is very easy to derail me with questions about this topic, just because it's something that I have found so fascinating and so interesting for so long. If you run across any interesting articles or videos or things recently, I've started a couple of discussion threads. They're not part of any formal assignment. They're not going to show up in one of the lesson modules for the distance ed side of things, but feel free to post them. It's just another way to stay connected and to stay thinking about the science that we see every day around us. I do want to keep it away a little bit from COVID posts, just because we're getting exposed to so much of that right now. And there's way more to science than epidemiology and virology, which is most of what we're seeing these days. So stay home, stay safe, stay healthy. I'll see you next time. Bye.